Students, hi, this is Mr. Bob, and these notes are about half-life under topic 7.2 and 12.2. And before starting this video, you should set up some focus notes. Again, you can do it by pen and paper, or you can do it in electronic version. The link is provided there, bit.ly/F, and it's a capital N, capital F, capital N template. And the essential question for today is, how can we mathematically model the decay of radioactive isotopes? So if you recall back to the radioactive decay activity you did, either the M&Ms in class or the coin flipping virtually, a key question you want to ask yourself is, were you able to predict when any one coin or M&M would decay? And if you think about it, the short answer to that question is no. Given many identical unstable nuclides, it's impossible for us as scientists, as observers, to predict when any one particular nuclide is going to decay. But the fascinating thing, well, first, in other words, the process of decay is random. We don't know when it's going to happen for any one given nuclide. But the fascinating thing is that if you have a big group, a very large group of them, then can one fairly predict how many coins within the big group will decay? And the answer to that question is yes, because even with a random process, if you have a large enough population, the probability that a certain proportion will decay in a certain time is well defined. And in fact, it's very, very exact. And we can model it and we can track it. And we have done so in laboratories. And we've noticed that we can mathematically be quite accurate with it. So how can we mathematically model this? Let's talk about a couple of ways. One very important concept that you want to remember is this idea of a half-life. And this is an important definition. The half-life of a particular isotope is the amount of time required for half of that isotope to decay into some other nuclide. This often gets written as you can see a lowercase t with a subscript of 1/2 or capital T with a subscript of 1/2. The T stands for time, half stands for half of the isotope to decay. Here are some typical half-lives, and they're arranged from, at least in this sample, from longest half-life to shortest half-life. And you can see here, for some of the things we've been talking about, uranium-238, plutonium-239, wow, these half-lives are incredibly long in terms of the number of years. If you look down towards the other end of the table, though, you can see that you can get half-lives that are just mere seconds or even fractions of a second. So there's a huge range in terms of radioactive isotopes, in terms of their half-lives, and that's something you should keep in mind. Cobalt-60 is another really interesting isotope. It's one of the ones that's most concerning related to when we have nuclear accidents, especially, for example, the reactor accident in Chernobyl in 1986 in Russia. Now, this is a useful equation that is not in your data booklet, and I'm going to spend a little bit of time on this equation because I think it can be really helpful. Notice what we have here is this is the number of nuclides present at time t. Present, I can't write well today, at a certain time t. This would be, n sub o is the original number of nuclides that you start with. Notice we have the 1/2 there, and then the 1/2 is raised to this exponent, and this exponent is really key. On the top here, you have the elapsed time, the problem that you're talking about. And on the bottom here is you have the time for one half-life. Okay, and we'll see if we can kind of apply this in the future. So again, this is not in your data booklet, but I have found in the past that students find this equation quite useful to keep in their mind. So if you think about it, the way this equation works is if I have the half-life of, if the amount of time that has passed is one half-life, then T over T is going to be equal to 1, right? And so I'm going to take my original amount and multiply it by 1/2, and I'm going to get the half of the original amount. If I have 2 half-lives that have gone by, then I'm going to have 1 over 2, right? 2 over 1, because the time will be 2 up here, and this will be 1 down here. So it'll be 1/2 squared, or 1/4, and I'll have 1/4 the original amount, et cetera, et cetera. Okay, so let's look at an example here. Suppose you have 64 grams of radioactive material which decays into 1 gram of radioactive material in 10 hours. What is the half-life of this material? You should pause this video and try and solve this problem on your own first. Okay, let's continue. So the solution. The easiest way to solve this problem is just keep cutting the original amount in half. So if I have 64 to start with, after one half-life, how much is going to be left? 32. After another half-life, how much is going to be left? 16. Another one, 8, then 4, and then 2, and then 1. Okay? So note, how many half-lives have I gone? If I count them, 1, 2, 3, 4, 5, 6. So I've done 6 half-lives in 10 hours, which is 600 minutes. So if I take 600 minutes divided by the 6 half-lives, I get 100 minutes per one half-life. Okay, and just to kind of show you this, this equation, let's go back here. And the equation I showed you previously, 1/2 raised to the t over t 1/2. In this case, what I would do is I would say the amount I have is 1 here. 1 equals 64 n sub o 1/2, and then the t is 10 hours, and then the t 1/2 is down here. Okay, so you'd have to solve this. Excuse me, I don't have the 64 there. There we go. Notice what you'd have to do is then solve this equation for the half-life there that's in the exponent. And you can do that with logs. I'm not going to go into it now, but you can see here that this approach with integral numbers, this is a much more straightforward approach than the mathematical approach that you see below. Okay, but it is possible to do it the other way. One thing I want you to keep in mind is that decays are often measured instead of nuclei. It's really hard for us to measure how many nuclei are left. Okay, but we can easily measure with things like Geiger counters that you see there when nuclide decays. And so often what we do is we measure the amount, we measure the decay rates instead of the number of nuclides, okay? And so decay rates are usually measured in something called becquerels. They get a capital B and lowercase q, and a becquerel is simply 1 decay per second. Okay, so if I have an isotope that is measuring 50 becquerels, that means on average 50 decays are happening per second when I take that reading. The other thing I want you to realize is because we measure decays, the half-life mathematical modeling still works because the activity, something we call activity is basically decays, is proportional to the population. So the decay rate of the activity is proportional to the population of any radioactive nuclide in the sample. So if my population nuclides, radioactive nuclides decreases in half, my activity is also going to decrease in half. Therefore, we can kind of synonymously move back and forth between those two. Okay, SL physics exam takers, if you're taking an SL physics exam next May, then the types of problems that you will get will always involve whole integer multiples of half-lives, like the one I just showed you. If you're going to be taking the HL level exam, then you may see numbers that are not so convenient. So let me just talk briefly about that. But first, let's do a quick joke. What did I say when my friend told me he was going to trick some nuclear researchers? That is a concern. I bet a lot of you are laughing right now. Okay, so for not so convenient numbers, okay, if you look in your data booklet at subtopic 12, this is in the additional higher level topics, you're going to see this equation here that I've circled. And notice I have again the n, which is the number of nuclides present at a certain given time t. I have the original number of nuclides present at the initial time 0. And then I have this e to the negative lambda t. Now let's make sure we understand what the lambda means. The lambda, this guy right here, is something we know that is the decay constant. And I'll talk more about that here in a moment. But this is an equation in your data booklet. And if you're an SL exam taker, you could also use it, but I don't think you'll need to use it. But let's go and talk further about what the decay constant means and how it's related to a half-life. So this equation, again, is another one that's not in your data booklet, but I strongly, strongly recommend that you commit it to memory. And that is the relationship between the half-life of a substance and the decay constant. Notice here, this is the decay constant. And basically, if I take the natural log of 2 and divide it by the decay constant, I get the half-life of the substance. So that's something you want to keep in mind, and I would definitely commit that to memory, especially if I was an HL exam test taker. Okay, let me just show you one more equation that's in your data booklet and just kind of demystify something about it. So notice here we have this equation, A equals lambda m sub o e to the negative lambda t. Well, A just stands for activity. And again, the most common units for that is decays per second, which is also known as a becquerel. What is this lambda n sub o? Really, that I would say is more commonly known as the initial activity. Okay, for whatever problem statement you have, you might get initial activity for the substance. Okay, and so you can replace lambda n sub o with a sub o if you're presented with that type of problem. And notice that it's very synonymous. This equation is pretty much the exact same as this equation, except you're substituting activity for number of nuclides, and we already talked about those two are proportional to each other. Okay, a few sample problems to finish this out. Here's one. A nuclide X has a half-life of 10 seconds. On decay, a stable nuclide Y is formed. Initially, a sample contains only the nuclide X. After what time will 87.5% of the sample have decayed into Y? Again, pause this video, try and work it on your own. Okay, let's look at the solution. Well, here's the it's a multiple choice question. You have 4 choices there. So the solution is we want only 12.5% of nuclide X to remain, right? So if we start out with 100% of nuclide X, after one half-life, how much is left? Half of that, which would be 50%. After another half-life, what's half of 50? Half of 50 is 25%. And then after a third half-life, half of 25 is 12.5. So how many half-lives have I had to go in order to get from 100 to 12.5? I've had to go 3 half-lives, right? So the time is 3 half-lives, or 3 times 10 seconds, or 30 seconds. Here's another example. Suppose the activity of a radioactive sample decreases from X becquerels to X divided by 16th or 1/16th of X becquerels in 80 minutes. What is the half-life of the substance? Again, remember, we have to remember that activity is proportional to the initial number of half-lives, or the initial number of radioactive isotopes. So we can just kind of use this idea that if I'm going from the original number, one half-life, I'm going to have half. Second half-life, I'm going to have a quarter of the original. After the third half-life, I'm going to have 1/8 of the original. And after the fourth half-life, I'm going to have 1/16th of the original amount. So how many arrows do you see there? 1, 2, 3, 4. So I have 4 half-lives in 80 minutes. And so the half-life for one half-life would be 80 divided by 4, or 20 minutes. Okay, and then finally, this is a graphical one. So the graph below shows the variation with time of the number of potassium-42 nuclei in a particular sample. And now what this wants to know is that potassium-42 decays into calcium. And it wants to know on the graph, draw a line to show the variation with time of the number of calcium nuclei in the sample. So go ahead and pause this video and see if you can talk through what that would look like on the graph. Okay, let's see what we got here. So the solution is this. Remember, the total number of nuclides in the sample has to be the same. So if I'm going to draw the one for calcium, here's what I would do. I would, down here, when at the start it's at 0, right? And all the way over here, it always has to add up to what the n sub o is. So this is going to be, the last number is going to be like right around here. And I'm just going to pick off a couple other points here. Half n sub o would have to be also half, so it'd have to cross here, right? Because half plus half would give you the whole number. The red curve and the black curve, what I'm trying to say is the red curve and the black curve have to always add up to be the same. So if this is 2 and a little bit down, this has to be 2 and a little bit up. This by now is 1, 2, 3, 4. This crosses here a little bit above 4, so 1, 2, 3, 4. So it's right here. So notice what I got here is I got something that looks like this. And I could just maybe draw one more over here to guide me a little bit. So maybe something like so. Okay, let's see what happens. Notice that. It's going to draw a curve here. Oh, look, I'm not that far off. Okay, so notice what you do there is you basically have to know that the entire amount of nuclides between calcium and potassium are going to stay constant. And as one decays, the other is going to increase in its concentration, but it's got to increase accordingly. Okay, so hopefully you can now answer that essential question of how you can mathematically model the decay of radioactive isotopes. Thank you so much.